All right, welcome, ladies and gentlemen, to lesson 4 from unit 4. This is the final lesson for this particular unit. We're going to find the derivatives of our leftover functions, in this case, the exponential and the logarithmic functions. We need to start off first with exponential base e. So an exponential function where the base of that exponential function is e, looking like e to the x. Oops. Now, I want to kind of look at the graph of this function to try to think about what the derivative is going to look like, because this is a pretty interesting function. The graph of e to the x looks a little bit something like this, where this goes through the point 0, 1. Now, if we were to try to think about the derivative of this function, the derivative is the slope at every single point. You notice back here, the slope is very small at negative whatever. But it's positive. This is always a positive slope. So somewhere back here, the slope is very small. And then the slope continually gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. And the slope keeps getting steeper and steeper as we continue to the right of this graph. And you start to notice that it looks almost exactly the same, as good as I can draw on this tablet. Well, that just so happens is the derivative. It goes through the coordinate 0, 1. The derivative of e to the x is e to the x. So using our calculus symbols here, we have d dx of e to the x is e to the x. This is a super interesting function because the derivative of the function is itself. I will put in here that you better pay attention to whether or not that thing in the numerator or in the exponent is a function itself. So if I was to say, hey, find the derivative of e to the 3x, using the chain rule says it's the derivative of the inside function, which is 3, times the derivative of the outside function, which is e to that exponent. So make sure you use the chain rule as you go. Things can look pretty ugly as you're going too, because you can go d dx of e to x cosine x. And now the chain rule requires the product rule inside, or use the product rule on the inside of the derivative. Okay, I'm going to leave that one to you. So this is our very first one. This is the easiest of them all. Next, we want to look at, well, what if it's not e? What if we have the function a to the x, where a is bigger than 0 and a is not equal to 1, because nothing works if those two things happen. I mean, it's not, if a is 0, then it's 0. If a is 1, then it's just 1 a whole bunch of times. And so we're looking at all other numbers. Well, in Algebra 2 and in pre-calculus, we discussed, or in trigonometry, we discussed the idea that we can change the base to any base that we want using a little bit of simple math. Well, it comes out simple exponential math and logarithmic math. We can say that a to the x is actually equal to e to the x times the natural log of a. So if a was 2, so if we had 2 to the x, it actually equals e to the x times the natural log of 2. Well, that's really nice, because now if I want to find the derivative of a to the x, well, natural log of a is just a number. So it's a number times x, so now we get to use the chain rule, which will tell me that it is e to the x natural log of a, blah, blah, blah. But what's really cool here is the derivative comes out to be a to the x is, the derivative of a to the x is a to the x times the natural log of a. And if we think about it as this, if I was to do the whole process here, oops, if I was to do d dx of e to the x times the natural log of a, Using the chain rule, we'd say this is the natural log of a times e to the x times the natural log of a. Well, we already know from this idea right here that e to the x natural log of a is a to the x. So we can replace it with a to the x, and we can rewrite this as this statement right here. So another good one to know is that if you have an exponential whose base is not e, the derivative of that function is going to be that exponential times the natural log of the base. But I will also mention that if x is a function, if that exponent is a function, you must use the chain rule. So always remember the chain rule here, folks. What about the natural logarithm? We're going to actually use some implicit differentiation and what we just learned in order to solve this derivative. So I want to find dy dx. So I don't know what the natural log, how to find the derivative yet. So I'm going to change this. We might remember that the natural log of x is equal to y, and therefore x is equal to e to the y. So I can change this to say e to the y, taking the exponential of both sides, is equal to x. And if I take the derivative of both sides, I get the derivative of e to the y. Well, y is now a function, so using implicit differentiation, we get y prime times e to the y is equal to 1. Well, then we could go like this. All right, y prime is equal to 1 over e to the y by dividing by both sides. But we don't have a function of x yet. But we know from this statement that e to the y was equal to the was equal to x. So the derivative of, this e to the y is x, so the derivative of the natural log of x, I don't know what happened there, is equal to 1 over x. So that's actually what I have here. We're using a little implicit differentiation. The derivative of the natural log is 1 over x. And again, I will mention, note that if x is a function, you must use the chain rule. So giving you some sort of an example here, if I was to take the derivative of the natural log of x squared, I would say, okay, the derivative of the inside is 2x times the derivative of the natural log is 1 over the thing on the inside. And I get 2x over x squared, which becomes 2 over x. Okay, so we just looked at logarithm base e, but what happens if I try to use the logarithm of a base a? So log base a. We're going to use the change of base formula here. Essentially. But what it comes out to is that the log base a, if you were to take the derivative, is 1 over x times the natural log of a. So this is a good one to have memorized. This shows up a little bit in our AP tests. So the derivative of any logarithm, so if I was to take the derivative of log base 2 of x plus 1, the derivative would be the derivative of x plus 1, which is 1. Oops, what's going on here? Gosh darn it. Okay, so dx of log base 2 of x plus 1 is going to be the derivative of the inside, which was 1, times 1 over that thing times the natural log of 2. And so we'd rewrite this as 1 over natural log of 2 times x plus 1. And there we would have our answer. But here's what we want to do. We kind of want to figure out how to find the derivative of x to the x. Well, we don't have a formula for it, but we do know some things about exponentials and logarithms now. But this is not base A either. Base A has to be a number, and x is not a number. X is a variable, so we need to take the natural log of both sides. So if I took the natural log of this and made it equal to the natural log of the other side, we can use our log properties to bring the exponent to the front. And now we have a product of two functions. So if I was to take the derivative of the whole function, of the entire equation, the derivative of the left is 1 over y times y prime equals, product rule, 1 times the natural log of x plus x times the derivative of natural log, which is 1 over x. And I need to multiply both sides by y, so I get y times the natural log of x plus 1, because x over x here. And if I know that y is x to the x, so therefore y prime is equal to x to the x times 1 plus the natural log of x. Which is kind of cool, being able to use exponential functions and logarithms in order to solve complicated derivatives. All right, I'm going to leave you guys with that. That will wrap up Unit 4. We have our test coming up next week, so make sure you guys are studying, and I will see you guys tomorrow.